is going on page 97 when we're done. So we're looking at inverse trig functions. So just like every other function that we did, we have inverses, right? And as with all functions, the inverse of a trig function is the result of switching the input and the output, right? You exchange x and y. That's what happens. So as a result, the output value of an inverse trig function will be an angle measure. So we've had their inputs be angles, right? We take the sine of pi thirds, the cosine of pi fourths, whatever. So our input is our angle. Since we're doing the inverse, now your output is the angle. That's the way inverses work, right? So the way we look at this, inverse trig functions can look like this or this, okay? You can say them both, as arc sine of x. You could also say that this is sine inverse or inverse sine. This looks like sine to the negative 1 power. If you were describing to someone how to write it down, that's how you could describe it. It is totally not sine to the negative 1 power. So we're going to pause and take a little side trip here and talk about sine to the negative 1 power, because that is something that we could have. Looks like this. Notice how the negative 1 is in a different spot, right? And then we know how exponents work. If I had 2 to the negative 1 power, that becomes 1/2, right? It's just the reciprocal. So sine to the negative 1 power would be 1 over the sine of x, right? That's what exponents do. And then dig deep back in your brain, because it's been a minute since we talked about it. What function is the reciprocal of sine? It's either secant, cosecant, or cotangent. Cosecant, good, because there's only one co in each pair. So sine to the negative 1 power is 1 over sine, which is cosecant. Now, these two things you could definitely see. You could see this, but you're less likely to see that. But either way, this is not that. Those are two completely different things. Okay? That's sine inverse. The other one is sine to the negative 1 power. Okay? And then again, the way you read it, arc sine of x, or sine inverse. So let's talk about inverses in general. I'm going to take this back, make this super simple. If I have 2 plus 3 equals 5, what is the inverse of addition? Subtraction, right? That's how you undo it. So 2 plus 3 equals 5, so then I can say, all right, well then 5 minus what gives me 2, so 5 minus 3 equals 2. Okay? And I flipped them around the equal sign on purpose because that's most of the time what we're doing when we write it here. You don't have to, but we're going to look at this. So we know that the sine of pi 6 is 1/2. As we put the input of pi 6, our output is 1/2. That's what we've been doing. So instead, what you're going to be asked is, what angle gives me a sine value of 1/2? And you can use the hand trick for that as well. So here's the hand trick, right? If I know sine is down here, this is my 1/2, this is my angle. So 1/2 for a sine value, my angle would be pi 6. All the values and stuff are the same, we're just going backwards, okay? So it's just like, what part are you being asked for? So since we know this, sine of pi 6 equals 1/2, then the sine inverse of 1/2 is equal to pi 6. That makes sense? It's just like 2 plus 3 is 5, but then 5 minus 3 is 2. It's the same type of situation there. Or we could write it as arc sine of 1/2 equals pi 6. Again, they mean the exact same thing. You could see it written either way, just depending on who wrote the question and what mood they were in, I guess. Now, this inverse stuff, not brand new to you, okay? We're going to take a little trip back to geometry here. So you don't have to write anything down. This is just some completed notes. When you first learn trig in geometry, you're doing right triangle trig only. And we are doing it to, you start off by finding missing sides of a triangle. So here we have the angle, which is 32. We have one side, and we're looking for another side. So you take the sine of the angle, and that's equal to a ratio of 2 sides, right? And then you solve it. That's how you get your side length. Once you get that good at that, then you get missing angles. Here, I want to know what theta is. I have 2 sides. They happen to be the adjacent and the hypotenuse. That goes with cosine. So cosine of theta, which is the angle, because it's always of the angle, is equal to the ratio of the sides. Then when you want to know, get cosine away from theta, you take the cosine inverse. So theta is the cosine inverse of this right here. Okay, that look familiar? All back from geometry. Okay, all right. So let's look. Oh, actually, I want to go back up here at the top. I'm going to rewind a little bit again. So I want you to draw this at the very top here. Make this pi halves, this pi, this 3 pi halves, this 2 pi, so forth. Okay? And I want to remind you that when we talk about quadrants, I do not care about the quadrants of that green graph that I just drew, because that's an x and y axis where my angles are on my x-axis, where I've kind of unrolled things, right? When we talk about quadrants, I care about the quadrants of my unit circle, okay? So if I'm going to go from 0 to pi halves on my x-axis on any of these graphs, that means on the unit circle I'm going from here to here. This is quadrant 1. When I go from pi halves to pi, that is quadrant 2. Pi to 3 pi halves, quadrant 3. 3 pi halves to 2 pi, quadrant 4. And then we start back over with quadrant 1, and it just keeps repeating, right? Because we're just going around the circle. So I want that fresh in your mind that, again, don't care about on the green graph or like the cosine and sine graphs that look like this. Don't care about what quadrant we're in. When we're talking about them, we're thinking about the unit circle. And it just keeps repeating. And it could repeat on, like, if this is 1, then this would be 4, and 3, 2, and go back the other way. Okay? Make sense? We good with that?
Doesn't need to start at quadrant 1, like it could start at pi, right?
Well, the axes are going to start at 0 no matter what. But yeah, the graph could start anywhere. Yeah. I'm just talking about how we're labeled on the graph. Okay. So back down here. Let's look at sine. So this is just a plain old sine graph that you have in front of you here. And because, all right, actually, let me rewind a little bit more. If I have a quadratic function, okay, just think about quadratics for a minute. And if I want to take the inverse of this, I can reflect it in the line y equals x. It would look like this if I just straight up reflected it, right? This is a function, this is not, right? And so when I take the inverse, if I want the inverse to be a function, I'm going to have to restrict the domain. That's why the inverse of a quadratic, when we're talking functions, is the square root function, because we have to restrict it, because this will not pass the vertical line test, but this will. Does that make sense? Remember doing that? So the other thing we talked about with this was so that I didn't have to draw this to check. I mean, there's algebraic ways to do it, but you know, visually, graphically, if I can reflect it, I can see, oh, that fails the vertical line test. Well, if I wanted to know if it failed the vertical line test before I did that, that's what the horizontal line test is, right? Notice how that's the same thing? So this passes the vertical line test, right? Does it pass the horizontal line test? No. So this function as it is will not be an inverse. That won't be a function, and we need it to be one. So that's why we are going to restrict, we must restrict their domains. So let's talk about how we're going to do that. Well, first of all, let's talk about sine. What is the domain of this sine function that we actually have? Or like, not just the one, but it's going to go on forever. So yeah, basically all real numbers. So negative infinity to infinity. Then what is the range? Close. Negative 1 to 1. Do I include both of them? Yes. Okay. All right. So when I invert it, I still need to be able to have all the values that I want to use for trig. So if I start here and I just do this part right here, okay, let's just look at that little curve. If I just use that little part, that gets me all of my positive sine values. Would you agree with that? All the values between 0 and 1. If I kept going, then I'm going to start repeating them, and that part would not pass the vertical line test, right? Or the horizontal, I mean. But if I go back this way to here, Now I have all of the negative sign values and all of the positive sign values. So I want to restrict my domain from here to here. I'm going to restrict this. What was negative infinity to infinity, I'm restricting it to negative pi halves to pi halves. Do I get to include those? Yes, because those are actual angles that I would need. On the unit circle, I am restricting this to the first quadrant and the fourth quadrant. But notice the fourth quadrant, we're not going from 3 pi halves to 0, because that's, 3 pi halves to 2 pi, because that's over here. We're going from negative pi halves to 0, and I'll talk a little bit more about that when we get there. Okay, everybody okay with that so far? So we have these restrictions. Okay, let's look at this. All right, so here's cosine. My domain, still negative infinity to infinity. My range, negative 1 to 1. Same thing, right? Because they're sinusoidal functions. So if I start off the same way I did with sine, this right here gets me all of my positive cosine values. If I go to the left like I did with sine, well, I'm repeating them. I don't want that. But if I keep going here, this curve right here will actually give me all of my cosine values. And that would restrict my domain from there to there. So for cosine, I'm restricting from 0 to pi. And I get to include those. On the unit circle, that means I'm restricted to the first and second quadrants. I'll show you in just a minute. First and fourth is the first one, yes, and then this one is first and second. Okay. All right, yes. Yes, yes. So we can have all, because they repeat on the unit circle too, right? That's why we're only using 2 of the quadrants. And if I asked you, so let's back up. We're limiting it for a couple of reasons. We're limiting it so we get a function and so that we only get one output. But if I look back up here, there's an infinite amount of angles that I can take the sine of and get 1/2, right? It can be pi 6. I can add 2 pi to that and add 2 pi. There's an infinite amount of them, right? But when I take the inverse, I don't want an infinite amount of answers. I want one answer. And so that's why we're restricting where we can actually get our answers from. Okay, and that might make a little bit more sense when we start to actually find some of the values. Just trying to figure out the restrictions right now. Okay, so then let's talk about tangent. So I'm going to start by sketching the parent function for tangent. Right, we know it looks like this, except I can't make a dotted line on this board. Okay. Now my period for the parent function of tangent is what? Is it 2 pi like for sine and cosine? No, what is it? Pi, okay? So that means this basically goes to pi right here. And you can see this really does get me all of my positive and negative tangent values, but my interval here gets split up by this asymptote. But if I draw this in here, like this, and I go from, so what would this x value right here be? If this is pi, what's this? Pi halves. And then what is this one? Negative pi halves. Good. So we're going to do like we did with sine and restrict this to negative pi halves to pi halves. Do I get to include those here? No, because they're asymptotes. And it says due to vertical asymptotes at x equals negative pi halves and x equals pi halves. And so on the unit circle, we're using quadrants 4 and 1, just like we were for sine. Okay? So sine and tangent use the same pieces, cosine's on our own. Okay. What questions you got at this point? All right, let's go look at some values and how all this works together. Here it says, it is important to always remember and consider domain restrictions. What we are doing today is pure math. naked math, meaning this right now, we're not applying to anything. Like, this is the skill, this is what you do. When we start applying it, it opens the door to some other things, but we have to look at the pure math side of it first. So that even though, yes, there could be those infinite number of answers, we get one right now from these specific ranges, and that's it. Those are our only options. So if I'm going to answer these questions about sine, if I'm going to take the sine inverse of something, the only angles you can give me have to fall between negative pi halves and pi halves. So I'm either starting here and going to pi halves this way, or I'm starting here and going to negative pi halves this way. Since this is included, negative pi halves could possibly be an answer, all right? Negative pi halves is at the same place as 3 pi halves if I have a positive angle, right? But 3 pi halves would not be an acceptable answer because it does not fall in this range. Does that make sense to you? So we have to go this way or this way right now, just because that's the way it is. Okay, we'll expand it a little bit, but like, that's it. I don't get to pick a different range. That's the only acceptable answers. For cosine, since my range is between 0 and pi, all of my answers will be positive. You will not give me a negative angle for cosine because we're going from quadrants 1 and 2 and it's going counterclockwise.
This is the same, except we're doing 4. I mean, 1. Okay, let's go with sine. Okay?
Mm-hmm.
We're using 1 and 4 quadrant,
Mm-hmm.
right? So it doesn't matter if it's like 2 pi, 1/2, right? Like, you get what I'm saying?
I do not get what you're saying.
Okay, so like a full circle is 2 pi,
Uh-huh.
right? So if could it be still in quadrant 1 but after 2 pi?
It has to fall between these two values on a number line. That's it. That's it. Those are the only acceptable ones.
I was going to say, so then within that domain, or that range?
The range of this output, my output, the answer to the question is going to be an angle. So that's why I'm showing you here. Like, even though, let's go here. Even though I know that when I do the unit circle, this, I could call this negative pi halves. I could also call this 3 pi halves, right? But when you're looking at a graph like this, here's where negative pi halves is. Here's where negative 3 pi halves is. So it literally can only fit between these two numbers on a number line. That's it. Okay? And it's because it's a function, you can't repeat your x's and have different outputs. Okay? So that's it. Okay? It's because we're making it into a function. Again, we're going to expand this, but when you are asked just purely what is the inverse, you get one option, and that's it. Okay? And that's the one thing that makes this a little, I don't know, if, weird or confusing. I mean, because what we're doing is really not that difficult. You just have to know what the restrictions are and know that you cannot get out of that. That's it. Okay? So if we go back over here, for tangent, I have the same restrictions I did for sine. Well, not the same because I'm not including them, but I'm going here and either going to pi halves or I'm going to negative pi halves. And that's it, and just not included. So although I know that there's an angle over here called 11 pi sixths, right? He'd be like right there. But 11 pi sixths, not an okay answer because it doesn't fall between this. It would have to be negative pi sixths instead. Does that make sense? That's what's happening, which is actually going to make answering some of these a little bit easier than it would if that wasn't the case. Okay, and I'll show you why. All right, so let's look at this. We're going to work through these with the process, kind of like we have going the other way. Meaning when I look at this at first, I'm ignoring the fact that that's a negative in there. And just want to know, so the cosine inverse of just square root of 2 over 2, ignore the negative. What that means, another way to think of it, is what angle gives me a cosine value of the square root of 2 over 2? What would that be? Pi over 4, okay? Now, this is negative. So if I'm taking the cosine inverse of something positive, my answer comes from the first quadrant. So if this was positive square root of 2 over 2, my answer would be pi fourths, but it's not. It's negative. So the negative has to come from the second quadrant. What is your second quadrant pi fourths angle? 3 pi fourths. Okay? Everybody okay with that? For cosine, it has to be, yes. Yes. Because then if I go the other way, the cosine of 3 pi fourths is negative square root of 2 over 2. Okay, that works just fine. All right, so now let's look at sine inverse. So let's just look at the positive first. What angle gives me a sine value of the square root of 3 over 2? Pi thirds, because you can use your hand trick, right? This is sine, this would be square root of 3 over 2. That's pi thirds. Okay, and if it was positive, it'd be pi thirds, but it's negative. So I'm going this way, which means it's negative pi thirds. See how that's actually easier than trying to figure out 5 pi thirds? You just slap the sign on it. Which is a coterminal angle with 5 pi thirds, but that's not the answer I can put there. Yes?
Just find out where its originally is. Find out the negatives.
That's it. Not for cosine, I have to figure out the second quadrant, but for sine and tangent, yeah, you just put the negative on it. That's it. Okay? All right, so tangent inverse. What angle gives me a tangent value of the square root of 3? Pi thirds. And it's positive, so it's just pi thirds. And if it's negative, it's coming from down here. Oh, and this will be negative right here. Okay, you kind of get the hang of it? If you know your values going forward, you'll be good. If you don't know your values going forward, you're never going to get it going backwards. I mean, that's why I've been trying to drill it into your head for so long, because it takes a while to solidify. All right, is arc sine any different than sine inverse? No. So what angle gives me a sine value of 1/2? Pi sixth, right? And this is positive, so my answer is just pi sixth. All the positive stuff comes from the first quadrant. Is sine also positive somewhere else? Yes, but right now we don't care, because we don't get to put answers from there. All right, what angle gives me a tangent value of 1? Pi over? Pi fourths. Okay, so pi fourths, but this is negative, so I'm going this way, so it is negative pi fourths. Now, the tangent of negative pi fourths is negative 1. The tangent of 7 pi fourths is also negative 1, but 7 pi fourths is not an okay answer, right? We're using the little reference angles there. All right. What angle gives me a cosine value of the square root of 3 over 2? Pi sixth, but this is negative. My answer is not negative pi sixth, because this is cosine, so I need my second quadrant pi sixth angle, which is 5 pi sixth. Good. Okay. So it's all the same values, and we're just going the opposite way, but we're very restricted on what we can use. What questions do you have at this point? Okay. Does that help kind of clear up the confusion on the front? Now, in the graphs, I mean, we show you the graphs so you can understand why it's restricted and what's happening, but really this is more the thing that you want to kind of see. You can say, all right, you know, just draw yourself little pictures of other things. All right, let's look at example 3. We're going to solve this. Now, this is an equation and it looks weird. That does not give you permission to make up math or quit, okay? It's got inverses in it, no big deal. We know we can solve equations. We also know that this right here is just some value, right? So I can go ahead and, I'm going to go ahead and rewrite the left-hand side, 1/2 times the sine inverse of x equals, okay, what angle gives me a tangent value of 1? Pi fourths. And since this is negative 1, what do I write here? Negative pi fourths. Good. Okay, now my goal is to solve for x. The next thing I need to move is the 1/2. Here's what we don't do. 1/2 does not become an exponent because this isn't log. Don't make up math, okay? You know what to do when you're solving an equation. What can I very easily and legally do to move that 1/2? Multiply by 2. So when I do that, this is going to give me sine inverse of x equals what? Negative pi halves. If you end up writing 2 pi over 4 first, that's fine, but it's negative pi halves. Okay. Now remember, the output of an inverse is angle. And that's what we have here. Sine inverse of some value gives me negative pi halves. But to solve this, I'm not actually taking the sine inverse of anything. I need to get this away from x. And the opposite of sine inverse is sine, right? So I'm going to take the sine of both sides. The sine of the sine inverse of x is x equals sine of negative pi halves. So negative pi halves is right here. What is the sign of negative pi halves? Negative 1. Okay. And the fact that that's negative 1 and this is negative 1 is a coincidence. Don't think you can just take the number out of this and be done. Okay, that is definitely not going to happen every time. All right, what questions do you have? We all good? All right. Let's look at this. Oops. So we've got the angle theta in standard position. I don't know why that's all there. And so here's my theta. It's in standard position. The terminal ray intersects the circle at point P, and these are the coordinates. Okay, got that. The points Q, R, and S are the result of the terminal ray being reflected over the y-axis, the origin, and the x-axis respectively. Okay, so that sentence, which sounds a little weird, but you're going to have weird sounding stuff in there. You just got to make sense of it. It's just telling you you're doing the reflections like we did with those triangles on the paper. If I take this point here and I reflect it here and I reflect it here and I reflect it here, then all of these little angles are all theta, whatever they are. Let's say theta is pi 6. Then all 4 of those little reference angles are pi 6, which means this would be at 5 pi 6, 7 pi 6, 11 pi 6, right? And nobody's asking you for the angles, but that's what all that nonsense means. Like, they're all related to each other. All right, so then for each of the following expressions, determine which labeled point intersects the terminal ray of the given angles. All right, we are going to label our ordered pairs. Even though I know this probably seems super easy, but you have to be careful on how this is labeled. Since this point is labeled xy, this point is negative x, negative y. I could, from the very beginning, make this point negative x, negative y. And if I say this is negative x, negative y, that makes this xy. Does that make sense to you? So you have to make sure you know, just because it's in the third quadrant doesn't mean you're going to slap negatives on the ordered pairs there. But in this case, because this is in the first quadrant, that is what's happening. So this is negative xy. This is x, negative y. Okay, so cosine inverse of x. If I'm going to do cosine inverse, what 2 quadrants do I get to pull answers from? Yeah, those are quadrants 1 and 2, right? So my only options are P and Q, only 2 options at all. The cosine inverse of x gets me to P, because that's where x is, the other one is a negative x. When I take the sine inverse, I only get to pull answers from first and fourth quadrants, right? So sine of negative y, or sine inverse of negative y, that would give me this angle, which would be S. Okay. I'm going to give you a second. You think through C and D. Okay, cosine, I know I can pull from quadrants 1 and 2, right? Cosine inverse of negative x puts me at Q. Tangent, I can pull from first and fourth. Negative y over x, that would be S. Okay. Notice we didn't look at R at all, because none of them have anything to do with the third quadrant right now. He's just hanging out waiting for us to figure all this out. Okay? What questions do you have? Are we good? Beautiful.